Hi, welcome back. We are still talking about Amperes Law, and I've got another example that I want to work through here with a coaxial cable. So let's check that out. All right, so coaxial cable is basically made up of two parallel cylinders or concentric cylinders. I've got my coaxial cable. We're going to say that it is infinite in length and it's oriented along the z-axis. And with a coaxial cable, you've got two conductors. So the inner one we're going to say has current I, positive I, and I've got the current going up in the z direction. And then the outer one has usually return current, which is minus I. So if you're unfamiliar with coaxial cables, that's how basically how they work. So you've got current I and current minus I in the two conductors. So I've got my red arrows pointing down in the outermost conductor, and we're going to say that the innermost cylinder has a radius A and it's solid. Then we have the outermost cylinder is like a cylinder shell, a cylindrical shell. It begins at radius B and it has a thickness T. And in between those cylinders then would be some sort of maybe dielectric material or free space. And the goal here is to determine the magnetic field everywhere. So we're going to find H everywhere. And when we say everywhere, what we really kind of mean, well, yeah, we mean H inside the first cylinder or the innermost cylinder, then H inside this maybe dielectric material or free space, then H inside the outermost conductor, and then H outside of the coaxial cable. So that is to say we're going to consider four pieces where the radius is less than or equal to A, where the radius is between A and B, where the radius is between B and B plus T, and then when the radius is larger than B plus T. Those are our four regions. And so you can guess almost that the Amperian path, or hopefully you can guess, that it's going to be a circle with the radius contained in the region of interest and centered at the z-axis. And that's because we know that a line of current has a magnetic field that swirls around the axis of that line. Okay, so let's consider region 1, where we're talking about inside the innermost conductor, right? So we're talking about this radius here. Now, in this case, you call our Amperian path L1, or whatever you want to call it, L H dot dl, like this. In this case, we're making a circle. Our Amperian path is a circle that is inside the innermost cylinder. Okay, it's in this region. So in this case, then, the current that passes through that circle, I enclosed, right, is going to depend on how big we make the circle. If we make the circle very small, then it's not containing a lot of current. But if we make the circle very big, then it's containing most or all of the innermost current. And we're going to assume that current is uniformly distributed here. So our enclosed current then, if it's uniformly distributed, well, what is that distribution? That would be the total current that is in the innermost cylinder, I, divided by pi a squared. So that, again, that's the current distribution then in that innermost cylinder. Then how much of that do we get from our Amperian path, or passing through our Amperian path? Well, that's determined by how big we make the Amperian path, pi rho squared. So you see it's a fraction of I that we get. All right, so we've got the left. We're going to concentrate on the left here and the right here, and the pi's of course cancel. Now we've done examples like this before, where we know that again H is swirling around it. That is to say, it only has a phi component. So we can write H, we know, is going to be some phi component like that. We don't know what it is yet, but we know it's in the phi direction. So when we do this integral, I'm going to leave off the L1 for right now. We've got h of phi, so that component in the phi direction, dotted with then dl as we go around our Amperian path. You know, we've done this in the first example in the last video. What's changing is phi, the angle, and so what is dl then? Well, dl is phi is rho d phi in the phi direction, like this. And so when we do that dot product, a phi dotted with a phi is 1, and we know that h phi, the magnetic field, is constant on a circle that's swirling around. And so what we get is that h phi can come out, the rho can come out because it's not a function of phi. And then we integrate phi from 0 to 2 pi. We go all around the Amperian path. And so this is just a constant. We tack on a 2 pi. And again, that's equal to the enclosed current here. And so if we solve for h phi, we get I rho over 2 pi a squared. Again, that's using the fact that it's enclosing this much current. I rho squared over a squared. And as that's the phi component, then we can say in vector form, this is I rho over 2 pi a squared in the phi direction. So that's what we get for situation 1 or region 1. Now let's have a look at region 2. And so now we're talking about in the material that's between the two conductors. That is a radius that's larger than A but less than B. Right? That's what we're talking about now. All right. Well, this isn't too bad. I'm going to choose an Amperian path that is, we'll call it L2 if you want, but it's got a radius. It's a circle, and it's got a radius in that range. So now h dot dl is equal to the current that the Amperian path is enclosing, but now all of the inner current is going through our path, since our path lies in this dead space material here, this dielectric or free space. Dead space meaning nothing's really happening in there. So it contains all of the current I. And if you work through the motions of what we did in the previous situation, where we said that h was constant and it only had a phi component and so forth, and then you do the integration, what you find, you find that the h phi can come out of the integral and the rho can come out of the integral. Then you tack on a 2 pi from the integration equals I, and then ultimately what you get is that h is equal to I over 2 pi rho times a unit vector in the phi direction. That's what you get. So interestingly, we see a difference here with the rho being in the numerator versus the rho being in the denominator. We'll say more about that in a little bit. Now we go to region 3, in which case rho is greater than b but less than b plus t. So we're in the second conductor now. So this is going to be similar to the first region, and we have to figure out what is the current that our path is enclosing. Well, we enclose all of the current in the first conductor, I, but how much of the second conductor are we enclosing? And we're going to add to it, but it's really a minus sign because the current is going in the other direction, as I explained at the beginning of this. So now we're going to figure out what fraction of I do we pick up from our Amperian path. So the total distribution in that shell on the outer, in the outermost conductor is I over b plus t squared minus b squared, and there's a pi there also, but I'm not going to draw the pi because that's going to cancel with this fraction here. So this is rho is the radius of our Amperian path, but then we subtract out b squared because b is where the cylinder begins, right? Just in the same way we subtracted it out here. So you have a pi here and you have a pi here, and they cancel, just like they canceled over here. And so this is the fraction of I then that we pick up from the outermost conductor. And so I will take it that you understand this geometry here of why it's rho squared minus b squared and so forth. And so this is the total current that our Amperian path is enclosing. This is again from the innermost conductor, and then the second term is from the outermost conductor. And we can rewrite this a little bit, just in a little bit friendlier notation, as 1 minus rho squared minus b squared over 2bt plus t squared, all that times I, if you FOIL that out. And then again, similar to the previous regions, we can make the argument that h only has a phi component, and then that's constant over our Amperian path. And so we get h phi can come out of the integral, rho will also come out of the integral, and then when we integrate we pick up a 2 pi, and so this is going to be equal to I times 1 minus rho squared minus b squared over 2bt plus t squared, like that. And then we can solve that for the phi component of h and then put it in vector form, and we see that h is equal to I over 2 pi rho times 1 minus phi squared minus b squared over 2bt plus t squared a phi, like this. So that is the third region. Now for the fourth region, when rho is greater than b plus t, I'll ask you the question, how much current would our Amperian path, which would be a circle of the right radius, a large enough radius, how much current would that path enclose then? Well, we have I from the first conductor and minus I from the second conductor, so we're enclosing a net of 0 current. Okay, and so from Amperes law, then that makes the magnetic field everywhere outside of the coaxial cable 0. So that's nice. So that has a lot of nice practical implications too. You can set up a long line of coaxial cable, and you know that it's not giving off any sort of magnetic field outside of that cable. Okay, so to answer the question then, determine h. So we could write a piecewise function here. I'm not going to rewrite all this stuff, but you would put this first box here, and you would put this second box here, and third and 0 there, right? And so we can do that. But we've essentially determined it all already. We could just group it nice if we wanted to. Also, what we can do is write or draw a nice little sketch. Whoa. Control Z. All right. We can draw a nice little sketch of our results, and this is called the profile of the magnetic field. So what I can do, and we saw something similar with the electric field intensity, I'm going to plot the magnitude of H versus rho as we get further and further away from the cable. And what we see then is, well, this first region, H, the magnitude, increases linearly with rho. So the magnetic field gets stronger and stronger linearly. Then we get to, and we could calculate the height of that if we plug in rho equals A, right? And then we get to the edge A, and suddenly then the magnetic field starts decreasing with 1 over rho. So that would look something like this. 1 over rho there. And then we get to B, edge B, and we could figure out what that height is by plugging in B here for rho. Okay, and then we get to region 3. And region 3 is kind of this goofy looking thing where we have this rho squared and we have this rho. So we could plot that on a calculator, or, and what you would see is it would be curved and it would go down to 0 actually when you get to uh, edge b plus t. And then once you get to b plus t, then it's forever 0 after that. So again, this is the profile. That's what we would say is the profile of the magnetic field as rho changes. All right, so I think that's all I have for you for Ampere's law, and we're going to continue then with magnetostatics.